Okay, thank you very much. Okay, welcome everybody to the SPM session on parametric surfaces. My name is Myung-Soo Kim at Seoul National University. I'm chairing this session. We have 4 super nice, excellent SPM papers in this section. And the first presentation will be high-order parameterization of discrete surfaces with local and global injectivity. Manish Mendet will present the paper.
Hello and welcome to my presentation on efficient piecewise higher order parameterization of discrete surfaces with local and global injectivity. This is a joint work with Professor Marcel Kempen. In the image, we see a parameterization that has been optimized for same distortion objective and on same underlying mesh geometry, but the key difference is on the left, the parameterization is linear within each triangle. Note that the isolines are straight and parallel, while on the right they can be curved. More specifically, given a triangle in 2D domain, we map it to a triangle on our mesh, and that gives us a linear parameterization. In a higher order setting, we define a Bezier triangle on the 2D domain and map it to our mesh. Hundreds of work have already considered the case of piecewise linear parameterization of triangle meshes in all detail in the past. Our goal is to see how one can efficiently combine all the techniques from linear settings and the benefits it could bring. So here's the problem statement. Given an input mesh, we want to generate a higher order parameterization such that it minimizes some given distortion objective under the constraint that map is locally injective per triangle, that is, the Jacobian determinant is strictly positive, or optionally globally injective. As is always the case for the overall total energy, either we truly integrate it over the domain or we use some sort of quadrature and approximate the energy function. So overall, we start from a piecewise linear initial parameterization with linear Bezier map per triangle. This can be, for instance, computed using tut embedding. We then raise it to a higher order setting and optimize. In this process, we need to constrain the optimization to preserve local or global injectivity, whatever notion is required in the specific use case. The first question that comes to mind is how do we initialize a higher order map which we can use during the optimization? This can be easily done by incremental degree elevation to guarantee that we strictly stay within the class of locally injective higher order parameterizations. And the reason is that a higher order polynomial can always be used to define a lower order polynomial. Now, what about the Jacobian? It is convenient to consider a map as being composed of 2 maps via a right triangle. The first map is simply an affine map between 2 linear triangles and will remain constant, while the Jacobian of the second map, J phi, can be easily built using the partial derivatives of the Bezier polynomial. The local injectivity can then be defined based on the determinant of the overall Jacobian. Since the first map, J psi, is always well defined, we only need to check injectivity for the Bezier map. We know that the Jacobian is a matrix of all first order partial derivatives of the map. And if we look closely at the partial derivatives in J phi, each of them is again a Bezier polynomial, but rather of order n-1. As a result, the determinant of the Jacobian will also be a Bezier polynomial. And for Bezier polynomials, we know that they lie within the convex hull of their control points. So all we need to do is check whether this range is strictly positive or not. In case it contains 0, then we recursively check for it by subdividing the triangle. And this gives us a very simple injectivity checking algorithm which we can use during the optimization. Now, to efficiently optimize the map, one can use Newton's algorithm, but that only works if its Hessian is a positive semi-definite matrix, which is usually not the case. In order to obtain a well-justified Hessian proxy that is PSD, we adopt majorization ideas. Given a function f as h of g, where g can be reformulated as sum of convex and concave functions g positive and g negative, via chain rule we can easily get the Hessian of f. Note that the first term is always PSD, but not the second one. However, note that g positive is convex, so its Hessian is PSD, and we also know that multiplying a PSD matrix with a positive number will again result in a PSD matrix. So in short, we ignore Hessian of g positive if it is multiplied by a negative factor And similarly, we ignore Hessian of G negative if it is multiplied by a positive factor as G negative is concave. This rule can then be extended if we decompose H again as sum of convex and concave functions, or extend it further if our function f is a composite of more functions like f of g of I. The two popular distortion objectives we considered exemplarily in our work are symmetric Dirichlet and as similar as possible. In both these cases, H is a convex function, and G, which represents the two singular values of Jacobian, can be expressed as sum of convex and concave functions in terms of the coefficients of the Jacobian matrix. For more details on other objective, when we apply this optimization,
it seems like this.
Yes,
Manish,
yeah.
It seems like the screen is not changing. It seems like the screen is not changing. Okay.
Is it okay right now?
Yeah, it's okay now. Right now, yeah. Okay, please go ahead.
In the higher order setting, we can already see visually that the map drastically improves. We perform several experiments to understand the behavior of this higher order parameterization. First, given a model, we optimize for symmetric Dirichlet energy with free boundary for linear, quadratic, and cubic setting, represented here in blue, green, and red color. The dot here in the plot defines the final energy relative to the linear setting, which is why we see the blue dot at 100. Then, we do it over the same model, but for different resolutions, namely 500, 10,000, and 100,000. And we repeat the same for multiple models. From the plot, we can easily see that the distortion benefit is more significant the lower the mesh resolution. We plot the same for fixed boundary and with 5 random point constraints to create scenarios with more inevitable distortion. Note that the distortion benefit is more significant the more distortion is inevitable due to constraints or surface curvature of input mesh. And finally, we can see that the jump from linear to quadratic setting is quite high, but not as much for quadratic to cubic. So one should use either quadratic or cubic. Going beyond cubic commonly has a negligible effect. Similarly, we do the same experiment for conformality promoting distortion objective under fixed boundary setting. One can see that the benefit for conformal distortion is much larger than the isometric ones. This actually can be attributed to the fact that isometric distortion objectives favor linearity, while curved elements can be optimal under conformality. In the beginning, we talked about the use of quadrature to approximate the objective function instead of exact integral. The more the number of quadrature points means better the approximation, but this comes at the cost of extra computation time. So a relevant question is, how low can we go while still maintaining proper optimization behavior? To figure this out, here we optimize for distortion objective for a given degree, quadratic in green or cubic in red, for different number of uniformly sampled quadrature points. Every line represents a different model which was optimized using different number of quadrature points denoted on the x-axis. On the y-axis, we see final distortion measured using a huge number of quadrature points. Note that the objective does not converge well enough when the number of quadrature points is too low. Our suggested number of quadrature points is 36 for degree 2 and 78 for degree 3. With these, we are definitely on the safe side according to all our experiments. To understand the runtime behavior, we do the following. Starting from a linear piecewise initialization, for instance from a tut embedding, we move to cubic setting via degree elevation and then run the optimization. The red dotted plot shows this timing. To improve the efficiency, we do optimization with incremental degree elevation. In other words, we first optimize the map under linear setting, then increase the degree, optimize for quadratic setting, and so on. We can see that this is much faster as compared to direct optimization. And elevating degree, when the relative change in energy goes less than 1%, is a good default. We have seen that higher order parameterization can be done quite efficiently with properly combining techniques, and that the results are beneficial in the sense that they exhibit lower distortion and, depending on the setting, much lower distortion. Nevertheless, of course, piecewise linear parameterizations are easier to use in established workflows. So it is interesting to see whether using one higher order piece instead of multiple linear pieces per triangle can perhaps be a better alternative. We do the following comparison. Given an input mesh, we optimize it for quadratic setting. Then we generate denser version of the mesh via subdivision and run optimization under the linear setting with free boundary. The plot here shows the progression of distortion during the optimization with respect to time. The earlier we get to bottom, the better, as it means the algorithm took less amount of time to converge, but also the lower we are, the better the distortion. And again, we run the experiment for 5 random point constraints to create scenarios with more inevitable distortion and for different models.
Thank you.
It can be observed that with an increasing number of linear pieces per element, the final distortion decreases. But to achieve a distortion as low as quadratic case, 16 to 64 linear pieces per element are necessary, and with those, the optimization takes quite a bit longer than for our higher order setting. In the paper, we also show how to handle seamlessness constraints. Here, the mapping is continuous everywhere except along cuts. But across these cuts, the map is related via a special class of rigid transformations such that the rotation part is always a multiple of 90 degrees. These parameterizations are used for generation and optimization of quad meshes and spline spaces. In our case, the cuts will be mapped to a curve instead of linear edges. To preserve seamlessness, we can employ hard constraints over the edges of our control polygon. The improvements in case of higher order are particularly obvious near the singularities. Additionally, we can also easily add penalty terms to the objective, pulling certain vertices to use a specified position in parameter space for 2D deformation. Here on the right, we see the mesh image in parameter space. On the bottom right, we see how visible artifacts due to piecewise linear nature vanish in the quadratic case. Finally, in the paper, we also show how to incorporate global injectivity constraints. This can be done via scaffold mesh to avoid any mesh intersections in the parameter space. The scaffold mesh is generated via filling and triangulating the entire ambient space with a fixed boundary. Then, local injectivity implies global bijectivity.
Anish?
The main task here is to maintain a nice scaffold mesh, which is usually done by Delaunay triangulation. After every optimization iteration, one can simply recompute a Delaunay triangulation in linear case. For curved case, however, one cannot use the same because no such fully robust meshing algorithm exists. So instead, we preserve the initial scaffold but update it to maintain a nice mesh. We update it combinatorially via Bezier edge flips, as well as geometrically, aiming for equilateral elements using a scale invariant conformal distortion objective. In short, for global injectivity, we iteratively optimize it for whole mesh, followed by improving the scaffold mesh quality. Given an input mesh helix here, the circular disk at the beginning is the injective initialization, and the following images are snapshot of distortion minimization that preserves global injectivity. We can also include user-defined penalty terms as shown for the gingerbread example here. Without global injectivity, on the right, we can see that both the examples shown here have overlap highlighted in red. Finally, we can apply it on the 2D monster example that we showed before, and we can clearly see that global injectivity avoids any overlap. To conclude with, we applied the concept of composite majorization in the higher order setting, enabling efficient second order optimization. We ensured local injectivity of the parameterization, which in the non-linear setting is a per point, not a per triangle property. We experimentally showed the benefit of using incremental degree elevation to improve the runtime performance. And finally, we extended the idea of using scaffold mesh for global injectivity by modifying it via edge flips and a conformal distortion objective. Our empirical focus herein was on demonstrating that abstract benefits in terms of lower distortion can be achieved using higher order parameterization. Further exploration of concrete practical advantages that result from this will certainly be of interest. Finally, more work can be done to improve the efficiency, for example, by choosing quadrature based on gradient of the Jacobian, providing higher continuity instead of just C0, guaranteed global optimum in case of global injectivity, and probably a better and efficient way to compute the inverse map. Thank you for your attention.
Okay, thank you very much. Can you turn on your video and microphone? Okay, this is time for question. Can you, raise your hand or send your questions to the chatting board? But in that case, I'll ask a question. Well, it's my impression that it will be quite difficult to extend this result to tetrahedral volumetric mesh. Is it really the case, or can you actually apply a similar technique, or what is your plan?
So we can
Future plan
apply
for-
it. We can apply it.
Mhm.
The composite majorization part that we explained, so that is not yet shown, like no paper has shown that part, but there is a different technique where they showed that using eigenanalysis that, okay, they can come up with a SPD Hessian matrix. So that can be used, and then the optimization will be very fast. So that kind of way can be used. And all we need to do is probably in the 3D case, we will have to use much more quadrature points. There was a paper from Matthew and Pierre like a few years back on curved Delaunay triangulation, kind of where they try to create as nice triangles as possible, so tetrahedrons as possible. So yeah, indeed,
Okay, so,
can be done.
Okay, so we hired Bartonet's question, so
yes, hello.
Okay, so go ahead.
Manish, could you say a little bit more details about the quadrature? You were saying that for quadratic you recommend, I don't know, 36 quadrature points, and for cubic 70 something. So is it about univariate integration? Maybe you explained that when the slides got stuck and I didn't get it, or do you integrate 2D domain?
So we integrated the energy over the whole triangle, let's say, right? But the Jacobian is not constant, so we cannot just simply multiply it by the area, right? So we need to pick it from a lot of points within the triangle and then sum it as the energy. So that's why we needed the quadrature. So we did very simple experiment that we have a lot of quadrature points uniformly distributed on the triangle. And then for different number of such quadrature points, we saw or we experimented how the energy behaves or how the algorithm behaves in the terms of convergence. And when it is too low.
So it is two-variate integration element-wise, right? But you sample the points and you somehow compute the weights, yeah? So this is a kind of Newton codes type quadrature when you prescribe quadrature points and compute the weights, not Gaussian type quadrature where you would have also position.
Yes. So in the paper, actually, we also compared with other methods that exist, but they were actually meant for polynomial kind of energy functions, and ours is more like a rational function. Because we have terms of like some function of p divided by some function again or q, and the problem then becomes is that they were using much, so even for a higher quadrature number of points in those settings, still the uniform was behaving better. So we rather chose this.
Okay, I see. Thank you.
Yeah.
Manish, you have another related paper to be published in this year's SIGGRAPH 2020. So can you mention the difference between the two results, or can you actually advertise your paper
Yeah.
in this year's SIGGRAPH 2020?
The main idea actually came from global injectivity. So over there I mentioned that don't have any robust method to triangulate given curves. And that is why we were like forced to maintain the same triangulation, but of course later on update it via edge flips and some conformal distortion energy. So later on we thought of how to extend it and create a robust algorithm for remeshing. So that paper deals with this part. So given some curves, we are able to triangulate the 2D domain robustly and with guarantees that all the triangles are injective.
But in the paper, you actually parameterizing the domain in the plane, right?
So in this one, yes. In the other one, it's
then,
just that given set of curves, we triangulate them.
In the plane.
Yeah.
Can you basically apply the same thing to sphere or ellipsoid or something like that? Or is that more difficult? I mean, constraint surface on
so maybe that will
slightly
be
more complex.
On that paper, but not right now, but that can be done too, hopefully.
That can be done, maybe for next year.
More like rational functions, this was meant to be polynomials only. So for rational function, we will need additional weights and then, extra one.
Okay, so is there other question? Okay, in that case, thank you very much. And then we will move on to the next presentation. Okay, thank you very much. So Ali, now you have the control. Okay, so the next presentation is minimizing toolpath generation for 5-axis flank CNC machining. And the paper will be presented by Ali Hashemian. Ali is currently the postdoc fellow at the Basque Center for Applied Mathematics.
Hello.
Okay, so Ali is here. Okay, yeah. So okay, so I can see your slide.
Yes.
Okay, yeah.
Okay, can I start?
Yes, please go ahead. Can you make the slide a little bit bigger? In my screen, yeah, the slide is a bit smaller.
But here is full screen, I don't know.
Oh, okay, okay. So please go ahead. Okay.
Yes. Okay, thank you so much for attending this presentation. That's a pleasure for me to be here in SPM conference. I'm Ali Hashemian from Basque Center for Applied Mathematics in Bilbao in Spain. The topic of this presentation is reparameterization of root surfaces toward generating smooth jerk minimized toolpaths for multi-axis phalanx CNC milling. The co-authors are Penge Bobo and Michael Bart. Okay, the toolpath in multi-axis phalanx machining is defined as the locus of the milling tool axis in the 3D space, which is the root surface. As you can see in the figure for a 5-axis phalanx milling, toolpath, which is shown in yellow here, is a trajectory of the rigid body axis of the tool. When the tool traverses the toolpath, sometimes it is going faster and sometimes slower. This is generally because of the toolpath parameterization when it comes from a CAD model, for example. And the parameterization may cause kinematic unsmoothness. So we want to reparameterize the root surface to resolve the potential kinematic issue of the motion. Especially here, we focus on the jerk of the motion. Jerk is the third derivative of the motion, where first is velocity and the second is the acceleration. So we want to minimize the jerk to smooth the motion of the tool during the machining procedure. As a motivation, I want to show a video here. The first step in machining is a roughing procedure that is faster with a lower accuracy. The second step is semi-finishing. You can see the tool is moving around the workpiece with some acceleration and deceleration, and there is many variations in terms of jerk. I mean the derivative of the acceleration. And here it's the finishing operation, the third one and the most important one. And yes, we should control jerk values over the motion, because if we have a variable jerk, it means that the tool has some impacts on the surface and some kinematic issues on the machine drives. Okay, starting with the definition of root surfaces. As you can see here, a root surface can have two boundary curves, let's say C1 and C2, that are in all case V-spline curves. And we have some ruling lines in the V direction. The rulings are of constant length, and we have a one-to-one correspondence between two ends of each line. And in equation 1, we have the parametric form of the root surface. As I told you before, it's a trajectory of the tool axis motion. And in equation 2, we have the B-spline representation of each boundary curve. And equation 3 guarantees that the root surface are of constant distance. And equation 4 is the first derivative of that, which is equations 3 and 4, both of them are the ruling constant criterion of the root surface. The objective of this work is to minimize the jerk, as I told you before, but more importantly, when we have an input toolpath, like what we have in the left in this figure, the tool positions are sampled uniformly in time with red cylinders, and sometimes, as you can see here, the tool may start going faster at the beginning and going faster at the end, but moves slower in between. This is because of parameterization. That is not always a good parameterization. So what we want to do is to, by minimizing the jerk through a reparameterization, we want to reach a smooth motion, as you can see with the green cylinders in the right. So you can see the motion is more smooth, with again with the uniformly spaced. So I think there was a problem, yes?
Yes, it crashed again.
So
okay. Ali.
I'm here. Yes, yes.
Yeah. Sorry about that.
Okay.
Okay, let's go ahead. Yeah, yeah.
Okay, so I finished this slide.
Yeah. Yes. Yes.
Okay, let's continue with our case studies. The first one is the Belisk benchmark workpiece, which is a practical industrial workpiece. And I showed this slide previously, but I want to emphasize again, we have a root surface given by given toolpath, and we have two boundary curves, C1 and C2. In the left, we have the initial one, and on the right, we have the optimal one. We want to minimize the jerk and find a a smooth motion on the path. So here we have two different measurements. On the left, we have 5,000 random sampling, because in many occasions, people have their initial values of the optimization as a random values. And if we go in this way, for example, with 5,000 random samples, our optimization may terminate somewhere else, not at the real minimum values we prefer. So you can see all the functions on the left are what we have from the optimization, but the objective function value are coming from blue to red. You can see we may terminate in somewhere else, not on the very minimum values. So what we want to do, we want to have only one optimization process instead of 5,000 optimization, for example. So our RDM-based initialization tries to find the best initial values for the unknowns, and then we perform the optimization only for one function. You can see on the right, with the magenta dots, we have initial initial transfer function given by the RDM, and then we find the optimal one that is very close to what we find from the 5,000 random sampling. And then we can play with control points of the curve to have a more accurate and better maybe reparameterization. So you can see here in this zoomed area that with different control variables, 10, 15, and 20, we have almost the same functions as what we have from random sampling. In this slide, we have the outputs of our reparameterization. On the left, we have the graphs of the norm of velocity, acceleration, and jerk of the motion with respect to time. You see, although our objective was not to minimize the velocity, but you see the velocity is more smooth. In the original parameterization, which was the input one, for two boundary curves, C1 and C2, we show them with blue and red lines. And you can see the dashed one is the original reparameterization, the original parameterization of the path, and the solid lines are all reparameterized one. You see that the velocity at the beginning and at the end was higher, but with our method is smoother, but I re-emphasize that the objective was not velocity, was to minimize the jerk of the motion, which is the third graph here. So, and again, you can see the jerk is very well minimized throughout the motion, but in the original path, it was higher at both ends. On the right, we have the vectorial representation of velocity, acceleration, and jerk. In reparameterization, the magnitude of velocity is changed, but its direction is kept and remained unchanged. But if we come to acceleration or jerk, we also have a variation in the direction of acceleration and jerk, but it's not very important for us. The most important for us is the value of that. The red one are the linear or original parameterization, and the blue one, the green ones are or optimized one. You can see almost throughout the entire motion, the optimal one are on a lower magnitude in terms of jerk, and as well in terms of acceleration. I re-emphasize that jerk is most important because jerk is the derivative of acceleration, and if we have a high values of jerk, it means that our acceleration is very oscillating and it has some impacts on the machine drive. Okay, in the next case study, we have the impeller benchmark workpiece, and we have two tool passes here. On A and B on the left, you can see the red are the original parameterization of the path, that is a tool uniformly sampled in time, but you can see the motion is not very smooth. It goes a little bit fast at the beginning and very fast at the end, and goes slower in between. But in the green one, you see the motion is very smooth. And again, this is the same case for C and D. There are two tool passes. The red is before reparameterization and the green is after that. Here, here on the top left, we have the transfer functions. The dotted magenta one is the initialization given by our proposed RDM metric, and the green one is the optimal one. And the dashed line is the linear or original parameterization of the curve, of the boundary curves, I mean. In the top middle, we have the velocity contours. The left is before reparameterization and the right is after reparameterization. So you see we have lower values of the velocity here, which was higher at the both ends. In the top right, we have the acceleration color codings. Again, you see it's better or smoothed after reparameterization. And on the bottom right, we have the jerk. So the jerk values are higher at both ends and it's very smooth throughout the motion. And here in the bottom left, we see the graphs of norm of velocity, acceleration, and jerk. And you can see they are very well smoothed with all reparameterization method. And in this slide, for the second toolpath of this workpiece, again, on the top left, we see that our magenta line, which is our initial transfer function given by the RDM metric, is very well optimizing because it's very close to the final optimal ones. It means that with very, very fast optimization with a lower number of iterations, we can very good find the optimal reparameterization. And again, in graphs in bottom left, you see the norm of velocity, acceleration, and jerk in terms of time. And again, you see the jerk is very well minimized, and the same for acceleration. But since the velocity is not the objective, the velocity is not very affected because the velocity is already smooth in the original parameterization. And on the color coding, you see on the left before and on the right after or reparameterization. And you see, for example, on the bottom right, the both ends are on a higher jerk, but after reparameterization on the right, we see that everywhere is blue. It means the values are very well minimized. So we can conclude this work. We have introduced a new jerk minimization algorithm for multi-axis machining. The algorithm looks for a reparameterization of the milling motion such that the jerk is globally minimized. We use the ruling distance metric, the RDM metric, that measures the distance between two finite lines in 3D space. This metric can be used for the initialization of the motion reparameterization as it captures the changing of the milling axis very well. And we have tested our algorithm on practical case studies and shown the proposed method quickly decreases the jerk, resulting in a smooth motion. As future work, we can use G-codes as toolpath inputs. Instead of using a CAD model, we can have G-codes because it's more common in the machining community. When the toolpaths are given in terms of G-codes, we need to know the direction and length of the rulings extracted from the code. And after that, our method can be applied to the B-spline path fitted on that boundary curves. And in our follow-up project, we deal with a physical validation that comes from G-codes, which is very practical example. And most importantly is the kinematic limits on the machine side, because what I showed in this presentation is to smooth the motion on the workpiece, on the tool path, on the tool trajectory. But more important is to do on the machine derives. From practical point of view, it is more relevant to optimize the jerk values on the machine derives. For this purpose, we need to fix the workpiece setup and going through an inverse kinematic transformation to convert the optimization function from the workpiece coordinate system, what we have in this presentation, to its counterpart on the machine coordinate system, and minimize the jerk values on the machine derives. That is more important. Okay, thank you so much for attending this presentation.
Okay, thank you very much. we have a question from Gershon Elba. So I turned on his microphone. Gershon?
Okay, I actually sent it on the chat.
Chatting. Yeah, but you can speak.
I will repeat it anyway. Can you go to slide number 4?
Yes, sure. Number 4. Yes.
Yeah, so the two constraints at the bottom forces the two railing curves to be at equal parametric distance and orthogonal to the ruling, and this is kind of restricted. And now when you look at the examples that you show in, like, for example, slide 15, it doesn't look like it's really orthogonal. So,
yeah, for example,
slide 15, go to slide 15.
Yes, yes. Okay.
It doesn't look like it's really orthogonal. So can you explain what you really do there?
Yes, sure. What we have in these equations 3 and 4, this is a ruling constraints. You know, in machining, we have a tool that is of constant length. So the ruling lines should be are of constant length. It means that in the v direction, between each C1 and C2, then the distance should be constant. And we have an equation 4 is nothing, just the derivative of equation 3, nothing more. So if you because this is the norm, this is a squared function between C1 and C2. So by deriving equation 3, we reach the equation 4. This is the ruling constraints. But it's not meaning that we are on the orthogonal representation between rulings and curves.
Well, it is if you obey completely what it says there. So I'm kind of a little bit confused because the examples are not showing that.
Maybe I can intervene. No, this is really just a derivative of the constant length constraint. Yeah, so it says that the projection of the derivative vector at one end is the same as the projection at the other end. Yeah, so you project these two velocity vectors at the ruling itself, and the projection is the same.
Right. So you're basically guaranteeing that the distances are the same just for the sake of what you're doing, even though the ruling does not have to be constant distance.
No, the ruling has to stay rigid. The ruling is rigid, so it is the milling axis, so it has to stay of the constant length. And the difference.
I'm talking about equation 3. Yes. I can have a ruling that is not constant, and yet you can take a subset that is constant. So what do you do exactly there?
Well, no, the ruling is the axis of the tool, so this has to stay constant. Yeah, it is a rigid piece. Yeah, so now I'm a bit confused about.
Well, I can have a ruling where the two rail curves are not constant distance.
I see. No, yes, as a ruled surface, of course, you can have, but such a ruled surface is not a motion of a rigid body axis. Yeah.
Well, but the cutter, the CNC toolpath can cut varying width essentially, but you restricted it to a constant width.
Well,
So here, Gershon, we assume that the milling tool always are on the full contact with the tool path, because what you mentioned is that sometimes maybe the contact with the tool with the workpiece is a smaller on a smaller width, and maybe the rulings are on the different lengths, as if I understand you correctly. Yes.
Yeah, I mean the ruling direction, exactly what you call rulings in your drawing here, could vary. They don't have to be fixed. I can have a cutter that remove different ruling lengths in different locations.
But because we are on the finishing stage, on the finishing stage, the tool is completely on the workpiece and on the full contact the workpiece, and the motion is very well controlled. So the assumption of having a constant ruling lines here is a correct assumption in reality, because here we have, I agree with your opinion, but in our case we have a full contact of the tool and workpiece. It means that we have constant rulings.
Okay, I understand what you're doing.
Oh, okay. So, okay.
Let's stop here.
Yeah. Okay, so because of our schedule, so let's conclude this talk. And then thank you very much, Ali. So because of all these technical problem, I think we have not recorded your the video of your talk properly by the system. So I would like to ask you to record your talks. Sorry about again, and then upload the talk, video recorded the talk to the Discord. Thank you very much.
Okay, you're welcome, and thank you so much.
Thank you very much. So, well, actually, Charlie also have some comment in chat, and then, yeah, so we will continue to the next presentation. The next presentation is multi-sided C2 B-spline patch of extraordinary vertices in quadrilateral meshes. Gerben, you are ready, okay? So you have the control.
All right,
Okay.
Can you see my screen?
Yes, yes, yes.
Okay.
Perfect. Thank you.
Yes, thanks for the introduction. Welcome everyone. I'm very excited to tell about the multi-sided C2 B-spline patch over extraordinary vertices in quadrilateral meshes. I'm Gerben Henninga, PhD student of UC Kosinka from the University of Groningen in the Netherlands. Right, so this is what we are going to talk about today. First, I'd like to introduce some building blocks, and then I'll go into the multi-sided cubic B-spline patches, show some results, and then we'll conclude. Right, in arbitrary topology meshes, we have very many regular regions, which for B-splines are not a problem, but the problems are introduced when many regular regions meet in an extraordinary point or vertex. And this generally gives problems in the definition of B-splines. Now, there are other solutions to or arbitrary topology surfaces, such as subdivision surfaces, but they are commonly only G1 at EVs or extraordinary vertices. Also computationally expensive. There are methods like Stam's method to evaluate the surfaces at arbitrary parameter values around EVs, but they also have their downsides. Now, many techniques have chosen to evaluate the irregular regions using multiple quadrilateral patches. This results in high degree polynomial patches, or also approximating patches, such as HC2. Then there's also another class of manifold surfaces. I won't go into detail about this, but they have a very theoretical ways. Other multi-sided patches, such as S patches, have also tried to bridge this problem, but they only can get G1 continuity at the cost of very many control points. And then there's also other control structures, transfinite control structures like the Gregory corner interpolator patches, which have been used in combination with subdivision surfaces before to fill in these extraordinary regions. Now, what we considered here is the generalized Bezier patch of Ferrari et al., which was published in 2016. This is a very interesting control structure, and well, we've always wondered, how can we update or generalize this construction from Bezier to the B-spline setting? And well, for this we introduce some of our building blocks. So to parameterize a multi-sided region, you commonly use generalized barycentric coordinates. So a quick recap of this is, if you have a point in a planar polygon, you can express this point as a linear combination of the vertices, and you get coordinates phi. And these coordinates are non-negative. They partition unity, so they sum to 1. They have linear reproduction, so they reproduce the point if you multiply the coordinates with their respective vertices. Have linear interpolation on edges, and they evaluate to 1 on the at the vertices. And of particular interest are Wachtpress coordinates, which are arguably the most simple generalized barycentric coordinates, which are well defined for regular planar polygons. Right. Well, these coordinates are of course also used in the generalized Behavior patches of Varadi et al. And generalized Behavior patch is a combination of n Bezier ribbons, which you can see around over here. So it's two rows of control points, and the surface is a combination of n of these partial Bezier surfaces. These partial Bezier surfaces, so the ribbons, are made from local parameters S and H, which are constructed from the generalized barycentric coordinates. And then there's also blending functions. So we have control points here, which are used in multiple ribbons. So to hold the continuity conditions on the borders of the patches, these have to be adequately blended. And well, the Bernstein polynomials, Bernstein basis functions, are used to multiply the control points to get a bi-degree surface. And well, there's also another thing, the weight functions of the combination of ribbons, they do not necessarily sum to 1. So this will give problems. So there's actually two strategies to solve this problem. First, you can normalize. You can just sum all the weights at a particular parameter value in the patch, and this way normalize the patch. Or you can introduce a central control point C, which is also highlighted over here, to which you can attach the deficient weight so that everything sums to 1 nicely. So how can we use this nice structure to create multi-sided B-spline surfaces? Of course, it seems natural to replace the Bernstein polynomials with the B-spline basis, but this in general will not work, and I will show this shortly. And another observation that you need to make is that if you have an extraordinary vertex over here, the surrounding regular regions are well defined for this ring of patches, but these patches are not defined. So this will leave an n-sided hole, in this case a 5-sided hole, where each side is adjacent to 2 regular patches. So if you want to construct a ribbon, you have to make sure that the ribbon continues over 2 intervals with respect to the regular patches over here. So this is why we constructed these extended basis functions. So in the top row over here, these ends, or the standard cubic uniform B-spline basis functions, here are the first 3. And you can see at the end of the interval here that the third function is non-zero over here. And this introduces problems, of course, because you want to have that the ribbon on each side, or the surface on each side, is only determined by its respective ribbon. So in this case, ribbons from distant sides of the patches, so on the opposite of the patch, will interfere with this. So what we did, we created the extended functions, which are the same for the first 2 functions, but the last function, we make sure that also at the end of the interval here, its value is 0, and also the first and second derivative is also 0, so that differentially it also doesn't influence the distant sides of the patches. And this is also true for the first 2 functions. So with these functions, we can now construct our B-spline ribbons. So over here, we have a B-spline ribbon for this side of the patch. So it's a 5x3 grid of control points. It's a piecewise C2 surface. So actually we have 2 pieces, which can also be seen over here. And along this parameter direction, so parallel to the side, we use the normal B-spline basis functions, and then towards the insides of the patch, we use these extended basis functions such that the ribbon will evaluate to 0 positionally and also differentially over here. And well, we also introduce blending functions like with the generalized Bezier patch. And well, for C2 continuity, which we are, or G2, sorry, continuity, which we are after, we actually need more blending functions than in the generalized Bezier patch. And they actually overlap, but this doesn't impose a problem on the continuity conditions. Actually, after everything is correctly blended so that we can get G2 continuity. And then the surface is a combination of, well, n of such ribbons, and well, the parameter domain has been multiplied by 2 to increase the extended domain of the patches. And of course, the patches are only C2 internally. More commonly, if you have multi-sided patches, they would be C infinity internally. But this time we have this piecewise nature of the ribbons, and this translates to C2 internally. Right, let's look at some results. So here we have a challenging case, as I would call it, of a hexagonal region, or a EV6. So at the top we have our multi-sided B-splines. You can see we have nice and smooth reflection lines, even at the EV. So here's the Catmull-Clark. And you can see the pinching artifact near the EV, which is absent in our reflection lines. Another case, heptagon. You can see everything is nicely smooth with the regular regions outside the patch, and also inside. Then we have also some arbitrary topology meshes. This is also interesting, because here you can see we have multi-sided patches, actually pentagonal patches, which are adjacent to each other, but still we get a nice G2 curvature continuity as well. Some other challenging cases. So we've implemented up to octagonal regions, which you can see here. And then one thing you might notice is that towards the center of the patch over here, you get a slight flattening off. You can also quite see it in the func-shaded renderings as well. And this is due to, well, the weight deficiency. Because, well, as I mentioned earlier, for the generalized Bezier patches, the basis functions of the ribbons, they don't necessarily sum to 1. And this is also the case for our, well, generalized B-spline patches. And this is what you can see here. So if we use normalization, you can see a slight, well, dimple in the center of this triangular patch. And we can use the central control point to kind of lift this up. But this requires some manual setting of this central control point, which is also something that you don't want. But in general, it's hardly noticeable, but it's still there. And of course, this effect increases for higher order patches, as you can see with the octagonal patch here, because when considering more sides, the weight deficiency actually increases. So there's less weight in the center of the patches. So more influence will be regarded to the normalization or to the central control point. Let's conclude this. One interesting thing to note is that there's different formulations of the extended basis function, and particularly the last one. There are many different ways you can set them, but they only need to vanish at the end of the interval, and it needs to be continuous with the uniform B-splines at the start of the interval. So there's many different choices for this. And one point that we would like to fix in the future as well is the weight deficiency. So how can we construct maybe these functions such that the weight efficiency is minimized as well, and still get nice shape. But all in all, this multi-sided B-spline patch is a very nice, simple control structure. We don't introduce many things. So it's a nice generalization from bi-degree B-spline patches to multi-sided faces. Well, they have good shapes, properties, and also continuity, so we can achieve G2 continuity with regular regions and also other multi-sided regions. And we can also efficiently render them through tessellation shaders. And of course, it should be possible to generalize this construction to other degrees. So maybe quadratic B-spline functions and higher degrees. And we're still working on that. And yes, I don't know how much time I have because I could show a quick demo of
yeah. Please go ahead. Yeah.
Okay. So I hope everyone can see this. So here we have a nice rendering of a arbitrary topology surface. So we have hexagonal regions and octagonal region and some triangles, and everything is rendered using tessellation. You can show over here. So everything is nice and efficiently re-rendered, and this is a very nice way of to render these surfaces. You can show the flexion lines as well. And here you can see also the dimple in the triangular surfaces. But this is quite absent in the hexagonal pieces. Okay.
Okay, very good. Thank you very much.
Yes.
Okay, so there is a question on the chatting board. The question is, are the resulting basis functions using GBC or piecewise polynomial splines?
Okay, let me see, grab the chat.
Yeah. There is group chatting.
Are the resulting basis function using GBC or piecewise polynomial splines? So yes, the basis functions are using the GBCs. So they are constructed from the, let's see, from these local parameters, SI and HI, which are made from the GBCs. And those are then used to construct the basis functions locally.
Okay, so maybe I may have just a very short question.
Okay.
What is the state of art for inside the tribate volumes? Do you have any, work on progress, or is there any?
Well, personally, I haven't looked into this, so I'm not quite sure about this. But I believe there's some people working on this. But personally, I don't really know.
Okay, so maybe quite a challenging problem, maybe.
Yes, sure, of course. Can only imagine.
Okay. Thank you very much.
Yes, thank you.
Maybe, yeah. Okay, so we will move on to the last presentation of this session. Thank you very much. So the last talk will be on global G2 spline space with improved geometric consistency with extraordinary vertices. The presentation will be by Professor Wei-Yin Ma from City University of Hong Kong. Okay, so I can see the agenda. Okay.
Hello. Good afternoon. Actually, good morning, good afternoon, good evening. So hopefully you can hear my voice. Yes.
Yes.
Yes. Thank you. So this talk is a joint work with Ma Yue, who is also here. So if you have any question later on, so we can also discuss. So this actually the objective of this talk is similar like the previous talk. However, we are using a different approach. So we are using I think the final resulting basis functions normally we are using Bezier basis, polynomial, piecewise polynomial basis. So first of all, so let me still come back to a few points in connection with this talk. Actually, what we are talking about is related to subdivision surfaces. So while we have a model of arbitrary topology, there are many advantages people would use subdivision surfaces. So, however, in connection with subdivision surfaces, there's a major problem is that in the region of extraordinary points, for example, somewhere here, so you have an extraordinary points with 5 faces, 5 edges connected to that point, which is not 4. Some other places is 3. So in such positions, the continuity condition is limited usually. However, for some applications, people of course prefer with higher order continuity. In the literature, there are also some constructive schemes where we could also achieve C2. However, the stencil is very complicated. In the literature, actually, there are also some other work, I think in connection to what we present here, people call patchworks. So in that case, actually, for the extraordinary region, for all the patches, so people filling that region, usually it's one ring extraordinary patches, using piecewise polynomial patches. So basically, it's a replacement or whole filling. Actually, this table you see, actually, there are also many different approaches. Some can also achieve C1, C2. I think it should be G2. So G2 at extraordinary position, and also allow the instance edges and also some other further areas. However, most of the schemes, as you see here, are not nested refinements. So which means that while we do further refinements, it's not nested refinements. So the the patches in that region after refinements may not be exactly the same as before the refinements. Of course, there are also some which can realize nested refinements, but of course, if you see the continuity conditions may not be there. And also in connection with some applications, for example, other geometric analysis, in terms of convergence, most of the subdivision schemes at this moment are can achieve only suboptimal, so which may not be very good for this kind of application. There are some which can achieve optimal convergence, but the continuity may not be there. So in any case, there are some restrictions for the moment. For example, like smoothness at extraordinary positions, or approximation properties, or implementation issues. I think the main purpose of this talk is mainly for constructing such a kind of C2 or G2 splice scheme. However, I think for this article, we are mainly for a bounded curvature subdivision scheme with least polar artifacts. Actually, it's a modified scheme of Kahneman clock. It's a tuned subdivision scheme which achieve better properties than Kahneman clock. This scheme can also achieve improved convergence for RGA applications. Of course, this one actually, if you see whether nested or not, however, for what we are presenting here, it's also not exactly nested refinements. However, we can achieve optimal geometry consistency. So which means that for any level of refinement where we apply this scheme, it's not exactly there, but it's optimized. I think that's what we want to talk about in this talk. In the following, I think we have more slides here, but I think we will mainly go through some of the main ideas. So first of all, as we mentioned, what we are developing actually is for a special subdivision scheme, which is called actually if you look at the stencil, looks similar like camera clock, but it's not the same. If you see the coefficients, actually they are optimized. It's a kind of a tuned subdivision scheme. This scheme, very importantly, that the subdominant values actually it's 0 or 0.5. So which means that if you use this subdivision scheme, while you do refinements, the meshes hopefully will be uniform, all the control points will be uniformly distributed while you do refinement for the extraordinary region, not like most other schemes. So we call ARPA subdivision schemes. So it's a subdivision scheme with least polar artifacts. It also achieves the better convergence properties. So our scheme is developed mainly for this scheme. However, it can also be extended for other schemes as well. For this scheme, however, due to the optimization of the parameters for the extraordinary region, we have actually 2 rings of extraordinary patches, not like camera clock, where we only have a single ring of extraordinary patches. So for this scheme, two rings of such patches. And the main purpose of this work is actually it's similar like the previous talk. However, we will fill in this 2 ring extraordinary surface patch, this whole with all polynomial splines, which we can achieve C2, G2 continuity. I think for this region should be G2. So that's what we have here. Basically, what we are talking about is that actually we will construct such a spline space where you see allow these edges where we can achieve G2. However, some other edges, it should be C2. So finally, with this kind of construction, all the basis functions for each of the control points, as you see, are similar like any other subdivision scheme. So each of the basis functions will be constructed as piecewise polynomial basis. So that's what we have here. So first of all, we need to develop all the constraints in order to make such a connection of the this extraordinary region. As we measured along all these edges, we apply G2 continuity constraints. So after some kind of reparametration where we can achieve C2, but of course, reality it's G2 continuity constraints. In addition to that, allow all these edges and also between all these patches in the secondary, and also allow all these edges between the secondary and the regular patches all are C2 constraints. So we need to develop all the constraints for maintaining C2 or G2 continuity conditions. In addition to that, actually, we also apply some other constraints for maintaining the geometry consistency between different levels of refinements. Actually, for this at this moment, actually, we fix some positions. At these positions, actually, we ask exact satisfaction. Later, you will see some other criteria where actually it's not exact fixing, but it's a kind of a minimization. And that with all these constraints, so I think in the article you may see details. Here we have a summary with all the constraints we have. And for such an extraordinary corner, so we need to figure out all the coefficients of the basis functions. And the final degree of freedom, we have still so many. And that we will fix the remaining degree of freedom after considering all the constraints by minimizing the energy function and also geometry consistency. So here this slide you see actually all the constraints we must use. So Cp equal Wq. So where P stands for the Bezier control points for all the basis functions. Of course, it's patchwise. Q stands for the local global control points. So that's a relation we must meet these conditions for the constraints, for the G2, C2 continuity constraints. In addition to that, as we mentioned, because we have also some other degree of freedom. So we optimize first for the energy, local energy in this region, in the extraordinary region. So where we have two ring patches. So that's the energy function. In any case, finally, is linear in terms of the Bezier control points. In addition to that, we also apply the geometry consistency. It's a colorful function. Functional basically is between different levels of refinements. We ask there must be a good match between such two levels. So this function we want to minimize. So after you find the differentiation, it's also linear in terms of the unknown Bezier control points. So finally, that's what we are doing. So we minimize, it's a combined function of the energy, local energy, plus also the geometry consistency we mentioned before. So with weights W here, subjecting to, so we minimize F, subjecting to all the constraints we ask. So most parts are geometric continuity constraints, plus also some exact satisfaction of the geometry consistency. Finally, this system you can convert to a linear system going to Lagrange functions. So that's the final linear system we have. If you see how this system looks like, so you have this C, P equal W, Q, where if you see Pi, these are the collection of the Bezier control points of the local, maybe we say local basis function or the local patches. And Qi, you see here, are collection of the global control points. So finally, we need to solve through all the basis functions through this linear system. However, all the basis functions actually are solved in a very simple way. So basically, for all the Qi you see here, be careful, each Qi actually it stands for the global control points of each of the sector. So we just fix one of them as 1, all the others as 0. So by doing that, actually the resulting surface you optimize actually is for a single basis function actually, corresponding to Qj. Here, for example, you see one of the basis functions at this position, so we call A2. So for this basis function, it's solved by assigning Q2 equal, I think this one, the index should be Q1. In any case, by assigning 1, corresponding 1 to 1, all the other to 0. And then you solve for all the Bezier control points for all the related patches. And that's the resulting basis function we produce. That's the basis function. These are the control points. And also with this scheme, actually, for all the basis functions we solve, actually we only need to solve the basis function for control points of a single sector, because all the others are symmetric, rotational symmetric. And then also we can guarantee so the partition of unity. So finally, actually the center basis function is produced by this equation for producing the partition of unity property. So in any case, all the basis functions are piecewise Bezier, actually piecewise polynomial, like this one for A2. And all the bases, we have a POU property. Here you see all the basis functions for valence n equal 5. We have solved for n up to 9. I think in the last few slides, just quickly going through a few testing. Here you see some sample control points from this article. We're actually from the websites there. Here you see the curvature plots just to show the local curvature, how it looks like. But all the results are G2, C2 continuity we have. This slide shows actually the geometry consistency between while you do the subdivision. So basically for our scheme, what we are doing actually, we apply the scheme in connection with a particular subdivision scheme. For this case, I think for our scheme, it's for the ARPA subdivision. So between any level of subdivision, you can apply this scheme. So whenever it's necessary. So we want to guarantee. So the resulting surface with C2 or G2, between different levels, we want to guarantee there's minimum error during the refinements. As you see, here is a comparison. I think specifically we compare one earlier scheme by Loop and Schaffer, which is this black curve here, and our scheme, this blue curve here. So what you see are here is the error to error in that over that region. So our scheme can improve very well. Here you see also some other cases. Actually, we apply the ARPA subdivision scheme without applying the geometry consistency. In that case, of course, in any case, I say if we apply, so we can improve the convergence. So here, this one I say it's with the infinitive norm. This one is with some other test with the geometric object actually using the basis functions we see in the previous slides. However, I think we just treat it as an object. Here you see also clearly the geometry consistency is very well. Of course, these functions are away from the extraordinary points, of course, because it's the same as regular baselines. So in that case, of course, not further improvement is possible. Here you see, lastly, just two examples we show here. For this model, you see some extraordinary points, and that's a resulting surface with a C2 or G2 continuity. So everywhere, regular or irregular regions. And here you see the highlight line display. If you zoom up normally, so I think the behavior is very good. So here is another example. I also want to mention here specifically, actually, you see actually for this column, actually it's produced using the Loop and Schaffer scheme using a Cameron-Clark subdivision. These two schemes, I think this is the final scheme with ARPA subdivision with geometry consistency, but this one without. First of all, what you see here is that first of all, you see the subdivision schemes are not the same. For Cameron-Clark, normally for n equal to 5, for example, at this position, so there's a problem with while you do refinements. So basically, it's not uniform refinements. However, if you see the meshes here, we use with the ARPA scheme, the mesh, no matter which level it is, so the mesh is always uniform subdivision, uniform distribution of the control points. So in any case, all of them, however, they are G2 or C2 continuity. I think that's all what we have here. Just briefly highlights. So we are developing, contracting global G2 subline space. However, maybe we should say it's mainly for whole filling of subdivision schemes. So which can be applied at any level for the downstream applications. We applied also discrete geometric consistency constraints with exact satisfaction. In addition, while we find the final parameters, we also optimize the energy and also the geometric consistency as well as the integral between two neighboring refinements. Very importantly, the final basis functions are represented in Bezier form. So it's explicitly calculated there already, which can be used for downstream applications. So this computation only need to do once. So once it's there, we can use in any future time. As for future work, I just mentioned 1 point. Basically, the contracts we're talking about here, it can be extended for any subdivision scheme using quadrilateral meshes. So for what we presented here, it only applied for the ARPA scheme we mentioned a few minutes ago. But the methodology can be extended to other schemes as well. And also the convergence, actually, yeah, I think that's all. Thank you very much. So if you may have any questions, thank you.
Okay, thank you very much. So we have time for questions. So we can check the chat board. Well, actually, I have one question. Well, it was my impression that the by degree 7 for patchwork is a quite high degree surface. But
yes, I agree.
Yeah. So, well, for visualization purpose, I think your experiment result are perfectly okay. But my question is, have you ever tried by degree 7 surface for other engineering applications like other geometric operations? What about the numerical stability or something like that in other applications?
We verified, for example, the convergence for other geometric analysis. I think for stability, hopefully should be okay. In terms of the high degree, so I agree that it's indeed degree 7 is a very high degree compared with degree 3 most of the times we are using. However, I think from some other articles, we will see that in order to achieve local G2 continuity condition, the minimum degree we can use is by 6. So we are using by 7. So minimum.
So, yes, so geometric stability is perfectly okay.
Should be okay.
Yeah,
I think should be okay.
Yeah. But it seems like in your literature survey, by degree 7 is still the highest in the previous results of patchwork. Is it really the case? Or nobody used any by degree 8 or 9 or higher?
I think I did not say. I think possibly most of the times the highest degree for the moment is degree 7 people are using, because if we use the higher degree, if you see the constraints, it could be very complicated. However, for lower degree, for lower degree people there are many articles. However, for G2, the minimum degree is by 6. However, there are many other schemes with by degree 5 or 4 or even 3. But in that case, not G2.
Well, anyway, 7 is a good number.
It's a good number. Could also try by 6. Could also try by 6.
Okay, thank you very much. And then, because of the our schedule, probably it's at the right time to conclude this session. Thank you very much indeed.
Thank you. Thank you all. Thank you.
Okay, let's thank all our speakers and then people attending this session. Thank you very much. Thank you.